All right. I think I've got technology good right now. I'm doing okay. All right, periodic trends. This is a biggie. They have a lot of stuff on periodic trends on the AP exam. Okay, this is a big hit item. So make sure that if you're not understanding something that I'm saying today, that you talk to me. Okay, ask me questions as I'm going through it. They like you to answer and reflect back on Coulomb's law as evidence that these trends exist. Okay, so hopefully you have Coulomb's law kind of solidified after doing the activity last night. Essentially, as you get further away from two objects that have an attraction or a repulsion, as you get further away, that force is going to weaken. That makes sense, right? As you get closer, they're going to strengthen. The bigger the force, the more attraction is going to happen as well. Or the bigger the force, the repulsion, if it's light particles. Okay? And we looked at that yesterday when we were looking with light particles about the oxygen and why that electron is slightly easier to remove. All right, so like I said, periodic trends are going to essentially come down to your Coulomb's law. Okay, so we've talked about the periodic table and how we've got our S block, our D block, our P, and our F. So you should be familiar with that. Elements with the same number of valence electrons tend to have similar properties. So excluding hydrogen in our first column, so everything below hydrogen are called alkali metals. As we move down that column, they're going to become more reactive. Okay, and we'll talk about that in here a few minutes. So those alkali metals, if you put them in water, you've done that before if you've had me for chem, okay? If you put those in water, they're going to sizzle and pop if you have a big enough piece. If you were in Mr. Goldie's class for that demo, he actually put too big a chunk in. It went up to the ceiling. He caught the ceiling tile on fire. It was a huge mess.
How come we didn't get
because I do not put that big of a chunk of sodium in water.
You should start doing that.
No. And if I were to put some, I would do it in the hood where it's a little bit more safe. Okay. Yeah. So these are your orbital diagrams. Some of you were asking me about that. We talked about this one specifically with oxygen yesterday. And how it's just a little bit easier to pull that one electron off because of the repulsive force there, because they're closer together, okay? And if we go back to Coulomb's law, the closer they get together, the more that repulsion force is going to occur. Now, why doesn't that happen in fluorine? Well, when we come over to fluorine, now instead of having 8 protons pulling those electrons in, we now have 9. So you've got 9 protons pulling that stuff in closer. Okay. So that is going to influence fluorine and why it's not as, we don't see that easier pull away from that electron. Okay. Now, in AP, just stating the trend does not give you points. Okay. So saying, as we move down, it gets more reactive. They're not going to give you the points for it. You need to tell them that as you move down the column, Good morning. Is it? Gotta go up to the attendance office and get me a pass.
They didn't give me one.
Oh, they give you the
They
tardy
scanned-
kiosk thing? Okay,
yeah,
we're
they
good then.
scanned my thing.
I don't know how they're doing that whole thing. I'm still learning the.
I heard it was 5 minutes, but I guess it's 15 because I like went
Well,
to go
first
buzz
hour-
in and they're like,
First hour, it's 15. It's different for first hour.
I did my homework.
Good. Okay. All right. So, like I was saying, as we move down the column, it gets more reactive. You have to tell them why. Okay. And that reflects back to Coulomb's law. As the distance from the nucleus increases, the force of attraction for that electron is going to decrease, and it's going to be easier to pull it off. It makes it more reactive. So that's why as we move down a column, those elements that are going to give away electrons are going to become more reactive. Okay. Now, as we march up a column, so if we want to put our thing here, as we march up a column here and get into fluorine, this fluorine is the most reactive nonmetal. Okay, remember, these guys are all full. They're satisfied. They don't need any more. Okay, they don't need any more electrons. Fluorine, though, has those 9 protons in the nucleus. That nucleus is very close, so it's able to go out and kind of grab those electrons from other things and pull them in. So that ends up being the most reactive nonmetal, and you need to reflect back to Coulomb's law. You don't have to say Coulomb because of Coulomb's law. You've got to explain Coulomb's law to them. So just saying, oh, as we move down the column, it can become more reactive because of Coulomb's law. No points. Okay? You've got to explain Coulomb's law to them. All right. So like I said, just stating a trend isn't going to do it. Just saying Coulomb's law isn't going to do it. You got to explain it. Okay. So when discussing periodic trends, talk about the charged nucleus, and you're talking about specific numbers of protons and also specific numbers of electrons. It's those valence electrons that you're concerned about, those outer electrons and the outer S and P. Coulomb's law then states that the attraction between two particles is proportional to the magnitude. So the more protons you get, the more force it's going to be pulling. So as we move across in the same row here, it's going to get more and more and more pull on the electrons because you're adding more protons in. Now, why does it get less down here? I've got 11 protons, and here I had 10. Why does it get less here?
Because they're further away.
They're further away. It's the distance. Okay? So go back to Coulomb's law. And you don't have to say because of Coulomb's law. Just explain it. Okay? Don't spend the time writing down the word Coulomb. Just get to explaining. That's the other thing. When you are doing FRQs in here, you are not trying to write an essay. You are writing, if you can write it in 2 words and get the explanation out, write it in 2 words. Okay? Make it as succinct as possible. This is not English. It is not social studies. I know in those classes for the AP exams, they want you to write nice, pretty, beautiful sentences. And that's great. Do that for them. For us, we'd run by different rules though. Okay? We don't want to, we already know you're smart. You took AP Chem. You don't have to prove that to anybody. Okay? Mm-hmm.
What's an FRQ?
It's a free response question.
So you want to be like, do you have to have full sentences?
Nope.
Or do you just want to answer the question?
Answer the question and move on. If you can answer it with 1 word, like if they ask you what element this is, don't say the element pictured, blah, blah, blah. Just write down silicon and move on.
Can you just write down like the SI?
Yep.
Okay.
You can write down SI and move on. Okay? Now, if they say explain, you need to explain. But you don't have to do it in flowery, beautiful DBQ language. DBQ is something.
Document-based question.
Yeah. Okay? You don't have to do it in that flowery language. Okay? For us, we want to see the answer, and we want to move.
So it's like SI comma
Because the distance is further, or because I have more protons, or what, yeah. Okay, and like I said, get to the answer and move. You're in a timed test, and you don't spend the extra time on that. Good? Because like I said, I know over there, and I'm not telling you to do that over there. For them, that's what you need to do, okay? So I'm not telling you that they're wrong. They are absolutely right for their field. For my field, though, it's different, okay? All right, periodic trends. Again, it's going to come down to attraction and electrostatics. Increase in charge, okay? You're going to have an increase. Increase with and it's going to decrease the force of attraction as you move further away. All right, first ionization energy. First ionization energy is the energy required to pull off that first electron. There's actually second ionization energy, and third, and fourth, and fifth, and until you get every electron ripped away. Okay? So first ionization energy is going to decrease as you move down a row. It's going to be easier to pull the electron away because the distance is increasing. So as you move down, it's going to get easier. As you move across, it's going to get harder. And this is all in the same row. It's going to get harder because you're adding in more protons. So you're adding in more things holding or pulling that outer electron to the nucleus. All right? Now, there are a few spaces where it doesn't appear to follow the trend. So here is your hydrogen and your helium. Why is helium more energy than hydrogen to pull it away? More protons, okay? But then I drop down here at lithium. Why?
Because
Distance is increased. I've added an extra proton, but because the distance is increased, it's not holding on to it as tight. And then we go up to Be, and then I go down to boron. Why did I go down here? Distance, yeah. Okay. So when you're looking at these, and I should draw this on the board for the video for Everett. No, it's not Everett in this class. Derek, yeah. So remember, this is your nucleus here. Okay. This is your 1s. Okay. I've got my 1s here. Then I've got my 2s here. Then I've got what? 2 P's. And they're going to be, come on, why are you not working? There we go. So I've got my 2 P's. Remember, they're peanut shaped. They're going to be here. They're very close to here, but they're just a little scunch out. Okay, so I've increased my distance just a little bit, and that's why it's just a little tick here that's down. Yeah.
Then why does nitrogen and oxygen if they're both in P?
Okay, so when I go to boron, I've got 1 here. When I go to carbon, I've got 1 here. And when I go to nitrogen, I've got 1 here. Now, when I go to oxygen, I am doubling up. I've got 2 electrons in that p orbital. Like charges do what? Repel. And these are in the same thing. So they're very close together. So as my distance decreases, my force increases. Okay, and that's a force of repulsion now, and it's easier to pull that electron away. Good. When I get to fluorine, though, and I double up here, now I've added an extra proton here, and I've got more pull holding that guy in. So that's why it continues, the trend continues to increase until we get to neon, and then we drop back down because we've added more distance. Our distance is increased. So it's easier to pull that electron away. Good? All right. So that's first ionization energy. When they give you, do I have this on here? Yeah. When they give you a problem like this is typically the type of problem that you're going to see. Okay. They're going to give you values for how easy or how hard it is to pull those electrons away. Okay. And what you're going to be doing when you analyze this is you're going to be going down this chart that they give you, and you're going to be finding where there's a big increase in energy. Okay. So between here and here, there's a big jump. Do you see that? Between 14 and then it goes to 7,700. Okay. You're looking for that big increase. And what that means is that you have gone back up a level. So if, let's see, this is what element here? This is magnesium. Okay. So we're looking at magnesium, which is this guy right here. Okay. So this is the 700 energy that we saw on that chart. This is the 1400. This is the 7700. Okay. It's going to take, this one's pretty easy to pull off. This one's pretty easy to pull off. This one is going to be really hard to pull off. Why? Why is it harder to pull that one off? Yep, it's closer to the nucleus. My distance has decreased, and therefore the force of attraction holding that electron has increased. Okay, so what you're doing is you're looking at this chart to try to determine where that is. And that was the extra bonus question on your quiz yesterday, I believe, had those different values on there. You had to be able to see where that jump happened. And based on that, you can tell what element it is. Because if you know that this increases, if we pull these two away, what charge is this guy going to have? Yeah, +2. Yep. So it's going to have a +2 charge. So what column of the periodic table has a +2 charge? Which column here would have a +2 charge? Yep, this one right here. Because if any one of these loses 2 electrons, they're going to have a noble gas configuration. So you're able to tell what charge it has, and from that, you can tell what column you're in. So these guys will have, except for hydrogen's a little funky, but let's just ignore him. He could have a +1 or a -1, so he's kind of weird. So just remember for the rest of these guys, these will always have a +1 charge. These will always have a +2. These typically will have a +3. It gets a little weird down in this kind of neck of the woods. They're not going to ask you about that. These always just end up sharing. They're like, oh, I just want to share. These guys have a -1, -2, and -3, except for some of the metals down at the bottom where it gets a little funky. But if they're non-metals, that's what it's going to do. Do you remember that from when we did ionic bonding back in the day? Okay. Any questions on ionization energy? Does that make sense as far as the repulsions, as far as how to read these charts?
Like if the 10,543 is the neon one, then why does it keep increasing?
So this would be your neon here.
That one?
Yep. Because it would have kicked back up. And then this would be your fluorine. Now they would have isoelectronic configuration. I can't remember the word. They're going to have the same electron configurations as these things. Okay. But they're not going to be those things. Because remember where does that get its identity from? The identity of the element comes from what? protons. Okay, so it's still magnesium. It's just magnesium with a +1 charge, with a +2 charge, with a +3 charge. It's still magnesium. It's just going to be isoelectronic, I think is the term for it. I can't remember the exact term, but anyway, it's going to have the same configuration as those things because it's lost the electrons. Am I making any sense to you? Have I just completely... Yep.
Shouldn't the higher numbers on the chart though be the ones that make it more energy to take away the electron? On the, or is it the lower numbers
I don't know what numbers you're talking about, honey.
on the ionization?
Ionization chart. So this is how much energy it's going to take to pull off an electron.
Then why does it take less for neon than for?
Because neon has, you've got, it's not really neon though, okay? Remember, this is still magnesium. So magnesium is going to have 12 protons, and at this point, it's going to be pulling on 10 electrons because we pulled 2 away. It's still magnesium, but now it's going to have 9 electrons. So it's getting pulled. It's harder to pull that away.
I thought it was changing the element.
No, it's not changing the element. We're not changing the number of protons. This is still magnesium. We're just pulling electrons off. So if we had magnesium, we've got 12 positive charges here. We're starting with our first electron level with 2 electrons. Then we've got our next one with 8. And then our outer one with 2. And what we're saying is we're going to start here and we're going to pull this electron off. We've still got 12 positives here. Okay? Then that's going to take this much energy to pull that electron off. Then we're going to pull the next electron off. So now I'm going to pull this guy off, but when I do that, I am changing the distance now. I've still got 12 protons here, but it's pulling on 10 electrons. This is how much energy it's going to take to pull off that electron. I've still got 12 positives. Now I'm here. It's going to take that much energy, and I can keep going. This number in the middle, the 12 protons, is not going to change. You might need to watch this video a couple times tonight. This is not an easy conceptual concept, okay? You might need to go out and watch other people's videos of me. Speaking of which, I did upload or give you access to the whole year of AP videos out on AP Classroom. And I posted the AP Classroom code, I think about a week ago on Google Classroom. So make sure you get in there. Those people know what they're talking about. So if you're still confused after this lecture, go and watch somebody else present it, okay? Sometimes hearing it from a different person, hearing it just a slight little tweak on it, it'll open up, okay? So sometimes you just got to listen to a couple different things for it. All right. Other questions about this one? You good on this? Are you able to wrap your head around it?
Yeah.
Okay. All right. So that takes care of that one. Atomic radius then. As we move down the column, the radius is going to increase. We're adding more layers. We're adding more levels. Okay? It's like an onion. It's going to get bigger. Shrug. As we move across, though, we're adding more protons. We're adding more electrons. Why in the world would it get smaller?
More attraction.
Right. You're adding more protons, so you're adding more things pulling it in. Until we get down to here. So if we're marching across, we get down to here, and now it's gotten bigger again. Why? I added more protons, I added more electrons.
distance because it adds.
Right, you've added more distance now. It's gotten further away, so that attraction isn't going to be as great. Okay? So, does that make sense in terms of atomic radius?
Mm-hmm.
That one, I think, is a little bit easier to kind of wrap around. And then this is the chart. Atomic radius smaller. We go up here. We get bigger because we're adding another layer. Then we're moving down, 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 down. We're adding more protons, so we're pulling in tighter. Then we jump because we've added another level. Okay, so that's the trend for that guy. All right, let me blow your mind again. Take a deep breath. Another sip of coffee. All right, so when we're talking about ionic radius, okay, right now I'm just gonna be comparing going across, and I'm gonna talk initially about metals, and then we'll come over here and talk about these guys. We're gonna start here. If I have lithium, I have 3 protons, and I've got my layer here. I've got my 1 electron out here. If I'm talking beryllium, I have 4 protons. I have my 2 electrons here, and out here, I've got 2 electrons. Good? If I pull 2 electrons away from beryllium, it's going to look like this. Yes? I have 4 positives pulling on 2 negatives. So it's going to pull them in tighter than it would this guy if I just removed 1 electron. Here I've got 3 protons pulling on 2 electrons. Here I have 4 protons pulling on 2 electrons. So this is going to be smaller than this guy when they become ions, because these are going to lose 2 electrons. These guys are only going to lose 1, because remember, they want to look like the previous noble gas. And these guys, if we looked at their electron configuration, now that they've become ions, what do they look like? If I just showed you the electron configuration for these guys as ions, what would they look like? They would look the same, and they would look the same as what else? What? Helium. Yes. Okay. So they're going to be isoelectronic, I think that's the term, with helium, because they've lost 2, they've lost 1, and they look like helium now. So as we move across this way in the same row, they're going to get smaller for their ionic radius. Now going down, they're going to get bigger because they've got more layers. Okay. All right. You got metals taken care of? You ready for non-metals? All right. Here we go. Now, these all want to look like what? What else is hanging out over here? It's not going to become an ion. Neon. Yep. They all want to look like neon. Okay. I have my fluorine. My fluorine has 9 protons. 2 here. I've got 1, 2, 3, 4, 5, 6, 7. Here I've got 8 protons. 2, 3, 4, 5, 6. And then nitrogen, I've got 7 protons. Okay. This guy, to look like neon, what does he have to do? Get 1 extra proton, right? You're gonna let me switch colors. Yes, you are. Good. So I've got one extra electron added in here. I now have 9 positives pulling on 10 electrons because I added one. Okay, so I've got 9 positives and 10 negatives. So this is going to be a little bit bigger than just plain old fluorine because I don't have as many things pulling on all those electrons. Now I march over to oxygen. What does he have to do to look like neon? Right, we have to add 2 electrons in here. Okay, now I've got 8 positives pulling on 10 electrons. Are they going to be able to hold that in quite as tight? No. Now I march over to nitrogen, and they've got to add 3 electrons. Now I've got 7 protons pulling on 10 electrons. They can hardly hold that thing together. They're way out here. Okay? So as you move across, the ionic radius is going to increase as you move from here to here. Does that make sense why? Okay. I told you. You had to take a deep breath for that one. All right. Electron affinity is just essentially like how the energy that's involved in trying to get, an extra electron. So how bad does fluorine want an electron? Real bad, like the worst. Okay. So that's essentially electron affinity. It's pretty much the same idea as electronegativity. All right. Now, electronegativity is really important. You got to understand this, okay? And you need to have a couple numbers kind of in your brain, okay? They're not hard to remember. Electronegativity is based off of fluorine. They actually, when they created this, fluorine became the standard, okay? And they just assigned a number to it. They said fluorine is 4. Okay? As we move down and all the way over to francium, we decrease our electronegativity. Francium doesn't want another electron. What does francium want to do? Get rid of it. Yeah. Okay? So, as we move across here, we're just going to subtract by 0.5. So this is 3.5, this is 3, this is 2.5. Guess what this guy is? 2. Okay? Hydrogen's the other one that you need to kind of know, and that's 2.2. And you're looking at the difference in these electronegativities. Okay? Now, the rest of these you don't need to know, but you need to just have an idea that as we move down, we're going to get less than 4. Less than this guy is going to be less than that guy, and so forth and so on. Okay? As we move across, so if you had to compare like aluminum with chlorine, you would know that chlorine is more electronegative. Don't need to know values, nothing like that. Okay? Now, why do you need to know this? Well, we need to talk about these electronegativity differences because that's going to determine what type of bond we're going to form or what type of character that bond is going to have. Okay? So, if we do electronegativity difference, so what are we doing mathematically? Subtracting. Okay? If we look at those differences, then that will determine what type of bond. So you guys have learned about nonpolar bonds back in the day. We're going to cover it more. We're going to dust off more of those cobwebs in Unit 2. Okay? You will have these solid, but for right now, you just need to know that we're going to come back to those electronegativities, and those electronegativities then are going to determine what type of bonds we're dealing with. Okay? Also, these electronegativities are generally what we use to write the order of formulas. So, for example, we don't write OH2. We write H2O because it goes in order of increasing electronegativities. So your hydrogen will have less electronegativity than your oxygen. Well, 2.2 is less than 3.5. Okay. There are a few things that are a little quirky, here and there. For example, we always write like ammonia is NH3. Well, nitrogen's bigger than hydrogen, so what? I don't know. I have no idea why. What I've heard people have told me, and I don't know if this is right or not, so don't write this down as gospel. But what I've heard is that this harkens back to like the alchemy days when they were doing all of that stuff, and they just keep it that way because of that. It's just the way it's always been written, so therefore we're going to keep it that way. I don't know if that is true or not, but that's what I've been told. All right, so questions about electronegativity. Fluorine wants it as bad as it can. Any element, they want an electron more than anything else. That's essentially electronegativity. All right, we are down to the and I forgot to erase these stupid things. Sorry. All right, higher first ionization energy. And I don't know if I can get these out of your eyes now. Okay, so we're comparing sodium or lithium and fluorine and oxygen. So which one has the higher first ionization energy? Sodium or lithium? So which one would be harder to pull an electron away from? Sodium or lithium? Lithium. Why?
Because
Coulomb's law. Go back to Coulomb's law. There, it's closer to the nucleus. Okay, so it's holding it on tighter. All right, fluorine and oxygen. Which one is going to be harder to pull an electron away from? Fluorine, because it has more protons. It has more of a charge in the nucleus pulling on those electrons. All right. Larger atomic radius, sodium or lithium? Which one's going to be fatter? Huh? Sodium. Why?
Because it's
gone up a shell.
It has more valence shells. Yep. It has more layers to the onion. Fluorine or oxygen? Which one's going to be bigger? Oxygen, because it has less protons pulling. Okay. Higher electronegativity, sodium or lithium? Which one wants to get rid of its electron more? Right, lithium's going to have a higher electronegativity. Yeah, higher electronegativity. Yep. So this one wants an electron. Yeah. Yep. And then fluorine wants it the worst. Okay. It has the extra proton. Yep. And the distance is small. Yes, ma'am.
I get why lithium is has higher electronegativity because the arrows, but why in the sense of Coulomb's law?
Okay. So we have so higher electronegativity means that it would want an electron more. So we would have our nucleus is closer. So here we've got the nucleus pulling. So if we had like something, lithium's not really going to want one that bad, just more than sodium. Okay. But if it did want one, okay, its nucleus would be pulling because it's only got this layer and this layer. Sodium has this, and this. So the nucleus here of sodium is going to be further away pulling on that electron versus here where it's going to be less distance. So always go back with these trends, always go back to Coulomb's law. Good? All right, you're going to watch the we do on the video. Scan the QR code, click on the video, watch it. This is homework. It is due on Tuesday because Monday you are going to have your first lab. Yay!
Is this due on Tuesday?
Yeah, that's due on Tuesday because you're going to have a lab on Monday.
Oh, this is the one. Okay.
Okay?
No, but I would like to do.
So, what I want you to do this weekend, go ahead and do the periodic trends homework if you want while it's still fresh in your head if you have time. Okay? But I'm not checking it until Tuesday. Did I not give enough? This is what I want you to do this weekend. I want you to read through this, annotate this, okay? Read through it. Know how to do the lab. Visualize it in your head, okay? If you are an athlete, a lot of times before you go into a competition, you kind of visualize, or like with your routine, I don't know, whatever you are. With your routines, you visualize in your head going through and doing these things, driving, anything like that. I want you to take this and I want you to visualize going through this. This you have done, if you've been in Honors Chem with me, you have done plenty of crucible experiments, okay? If you haven't, look up one of these labs on YouTube and watch somebody do it, okay? Good? Everybody happy with Lippy? All right. Yes.